A little bit different. This meeting's a little bit, session's a little bit different to the session I usually do because it's an introduction. And so what I plan to cover is more about how you do a performance study and the things that you need to think about as part of that. And then we'll talk a little about CPU memory, I/O, and network. As usual, I have way too many slides for the time frame, so some of the slides we will just very quickly be touching on. So with that said, one of the first things you have to figure out before you actually look at a performance problem is what is it that you're actually measuring. And there's two kinds of performance that people think about. One is response time based, the other is throughput based. So if you think about response time, it's from the time, as an example, that you hit enter till the time something comes back. Or it might be from when a request is submitted till it comes back. So that's a little bit different to throughput, which is how much can I get through in a particular amount of time. One of the things that's well known about the power systems is they are really designed for throughput. Response time is part of that, but they're really designed to do a lot of things at the same time. That's one of the things that things like SMT get for you. So typically we're going to be looking at throughput-based things. So then you have to think about what are the kind of things that make the system go slow. And there's certain things that are very obvious. Not enough CPU, not enough memory, you may not have enough disk bandwidth, and that can be caused by adapters, adapter queues, not enough disks. You know, you've got to be able to spread your I/O around. And there's a number of other things, including error reports. One of the things I see a lot when people are having problems is that they don't go and look at the ERRPT output. And if you're having an I/O performance problem and you see an ERRPT that you've got fiber adapters where the links are failing or disks where they're failing, that's probably a good indication as to where your problem is. So it's best to look there before you open a PMR. Something else that a lot of people miss in the shared processor pool is insufficient CPU entitlement, or even with dedicated cores, insufficient CPU. The obvious thing that it affects is CPU performance, but what a lot of people don't realize is that your shared Ethernet adapter and your virtual Ethernet adapters are all impacted by CPU. If you don't have enough CPU and or memory, then your network performance is going to be very poor. Because keep in mind that anytime you see virtual, which is like virtual Ethernet or the shared Ethernet adapter, which is built on virtual Ethernet, somebody has to be doing the work. And that's CPU at both the VIO and the client, as well as they have to be built in memory. Then there's the not so obvious, like AIX tuning. For things like Oracle DB2, there's buffering. Read versus write characteristics are important. If you have a workload that's 100% write, or even 90% write, the kind of disk performance that you're going to get is going to be very different to if it's 20% write. And then there's a number of other things that are listed here. So just keep in mind that these are all sorts of things that could impact your performance. All right, so I always say before you start, take a deep breath. One of the things that you want to do anytime that you're looking at a performance issue, or actually even when you're planning to make changes to the system, you should have a standard baseline that you use. Now, it can be whatever works for you. Mine is a combination of three things. I run a perf PMR, I run NMON 724, so I have a history of NMON reports, and then I have some scripts that gather some additional information. So I always take a baseline, and that baseline I run beforehand so that I have something to compare to afterwards to see what changed. That's also very helpful if you're trying to report a problem to IBM, because if you have a baseline before you caused the problem and then a baseline after the problem occurred, you can send both of those in, and IBM has now information that helps them to solve the problem. Right? But without that baseline, you've got nothing to compare to. This slide here is just showing you the flags for using NMON. This first one gets a 30-minute NMON, and the one I run 24 hours is this one down here, where I do every 150 seconds and I do 576 snaps. I kick that off at 11:59 p.m. every night, and I just run it out of cron. It's important to have a plan. I see a lot of people jump into performance tuning without actually having a plan. And so the key thing, if you're gonna write a change control document, normally you have to tell them what it is you're doing, why you're doing it, and what you expect to accomplish. And that's what this is all about. Describe the problem that you're trying to solve. Do your baseline. Can you recreate the problem? If you can, then obviously you do that while you're getting the data. Analyze the data. Then you have to figure out what changes you want to make, what you think will happen. And one of the comments I have here is, remember that one small change only you know about can cause significant problems. I actually, many, many years ago, worked on a problem with a client where it was on the mainframe, where literally their banking systems kept going down with corruption in their database. And everybody said they'd made no change, Well, it turned out somebody had changed a parameter in a piece of code, and that was what was causing the problem. So that's why I make the comment that all changes need to be documented, even ones that you think are completely and utterly insignificant. The other thing that you'll run into is people want you to make one change at a time. And that works for some things, but there are certain changes, like if you're trying to tune memory, if you're trying to tune the network, there are changes that go together as a group. So you need to group them together so that it makes sense. Then obviously the next step is measuring the results and going, well, did I get what I expected to see? And if you did, that's great. If you didn't, then you need to understand why not. And sometimes, by the way, you get better results. The other thing to keep in mind is that tuning is an iterative process. By that I mean you may have to do it 3 or 4 or 5 times to get everything. So it's kind of like an endless loop. And the comment I haven't read about this looking like, it's obviously common sense or what we call motherhood and apple pie. What I've found is that in an emergency, when you've got 4 vice presidents standing behind you saying, fix it, the first thing that goes out the window is common sense. So that's why it's important to find somewhere that you can focus and to try to nominate somebody, if this is a critical problem versus just a general tuning exercise, to have somebody in the team who's responsible to report back on the status so that you're not getting interrupted every 5 minutes. Because I don't know about you, but when somebody's asking me every 5 minutes, have you fixed it yet? It's never going to get fixed because I can't think. All right. So I've got a bunch of little flowcharts here, which are sort of some different methodologies that you can use for performance tuning. I'm not going to go through them. They're just there for you to look at. But it basically talks through sort of the steps that I talked about above. I threw this one in because it's kind of amusing. It's the one where basically people just pick something at random and then, that's obviously not what you want to do. And then there's another one here which is a full-blown, more of a full performance analysis chart. All right. So now we're going to move on and talk a little bit about CPU. Then we'll talk about memory, I/O, and network. And we're going to sort of go through these fairly quickly. So there's a number of terms that you need to understand. I'm not going to go into these in detail, just sufficient for you to understand that when we talk about a process, we mean a script. It could be a thread. It's something that is started with a command and is running to do something. In terms of the run queue, what we're talking about there is that every core has a dedicated run queue, and that's a list of all the runnable threads sorted by priority. Additionally, there is a global run queue, and when I talk about dispatching later, I'll talk a little about the difference between them. And I'm going to get into these other things in a little bit. I will mention with the time slice, the clock tick is 10 milliseconds, and so what you'll see is that that means that a dispatch window by default is 10 milliseconds, and we're going to talk about like how you can impact that. In terms of monitoring CPU, you can look at user, system, wait, and idle time for dedicated LPARS, and mostly you're going to look at user and system. For shared processor LPARS or dedicated donating LPARS, they're not actually that useful. because user and system are basically a measure of the percentages for the amount of core that was allocated at that time. The issue with that is that it changes. So what you have to look at is CPU cycles, or basically what we call PhysC. You'll see it called PC or PhysC in your shared processor reports, and it stands for physical consumed, and that's actual physical CPU. It'll show up in a number of these commands. You've got the LPARS stat, MPstat. There's a whole bunch of commands you can use. This EMstat is used to look for old code. What you'll see is emulations and alignments. What that means is there's a piece of code running that was designed or compiled on an older architecture. You're now running it on a newer architecture, and things like the alignment boundaries have changed, or some of the instructions no longer exist, so they have to be emulated. So if you're running EMstat and you see things in there, that is going to affect your performance, and it can affect both CPU and I/O performance. tprof, gprof, all of those are different kinds of traces for tracing applications, and there are many, many more commands that you can use for monitoring CPU. Something that's important to understand is the difference between dedicated cores and shared processor cores. So what I'm showing you here, if you look at LPAR 1, it is an LPAR that has SMT turned on. We're just doing SMT2 as a simple example. So I have 4 logical CPUs. Each of those logical CPUs represents an SMT thread. I have 2 cores assigned to it, so I gave it an entitlement of 2 with virtual. So I gave it 2 virtual processors, or real processors in this case. Under the covers, even when you're dedicated cores, there are virtual processors. The difference in the dedicated world is that each virtual processor has a one-to-one relationship with a core. So when that LPAR is brought up, each virtual processor, which will show as like proc 0, proc 2, etc., will have a one-to-one relationship with that core for the whole time it's up. So whenever that virtual processor gets dispatched, it goes to the same core. Now if we look at LPAR 3, in this case we gave it an entitlement of 1.2, which is this PU, and it has 2 virtual processors, which we assigned it. So it still has 4 logical CPUs. Again, it's an SMT2 example. Because we gave it a 1.2 entitlement, each virtual processor is worth 0.6 of a core, or approximately 6 milliseconds. Now the way those virtual processors get dispatched is at the time that the LPAR is running, the virtual processor will get dispatched to one of the cores in the shared processor pool. The system always tries to dispatch it to the same core, but there's no guarantee that it can do that. The other thing that you'll notice about this is, in this example here, the processor units add up to 1.2, which is greater than 1. So each of these virtual processors will get dispatched to a different core. Now if I look at LPAR 4, and don't worry about the fact that SMT is off, when I sum up the virtual processors, right, my entitlement is 0.8. 0.8 is less than 1. So they could get dispatched to 2 different cores, or each of these virtual processors could get dispatched to the same core, one after the other. This is one of the reasons why you'll hear me say later on that shared processor pools are good for most workloads, but if you have things that are latency sensitive, you may want to consider making them dedicated so that you don't run into the situation where I could get dispatched to the same core. So that's the point that I was trying to make there, is just making sure you understand one of the differences. Now simultaneous multi-threading is basically the feature that IBM added that assigns threads to each virtual processor. And you could have 1 thread, 2 threads, 4 threads, or nowadays with Power 8 and above you can have 8 threads. And it's all about throughput versus how long you can run on the core. So what IBM did was they duplicated some of the registers. So if you have a very varied workload, then what you'll find is that if you're running in SMT mode, and the workload is SMT friendly, you're going to get a lot more throughput out of the system. There were some things that changed. With Power 5 and Power 6, a single thread could actually consume 100% of a core. As of Power 7, it can't exceed 65% before it kicks off some other work. And the way that it dispatches things is going to vary depending on whether you are Power 6 and lower or Power 7 and above. So the key thing to remember about SMT is that it's all about throughput and getting as much workload through. Think of it as like a multi-lane highway versus one of those express lanes, where, you know, in that express lane, if someone has an accident, nobody's going anywhere. In the multi-lane highway, if there's an accident in one lane, everybody else can still keep working. Oops. So when we look at SMT utilization, there were some changes that happened. If you look at Power 6 and Power 7, in Power 6, if one thread was 100% busy and the other thread was available to do work, it reported utilization as 100%. In Power 7, they actually changed it, and the idea was to show you what the potential spare capacity was. And again, they refined it with SMT4 and again with SMT8, and they've tweaked it a little bit with SMT9. So I just wanted to point that out. The other thing to keep in mind is some of the uplifts from SMT, because they changed some things with Power 9. So it used to be that we didn't really bother so much with SMT8 because on a Power 8, the performance improvement was from SMT4 to SMT8 was only about 7%. Now with Power 9, it's more like 26%. So if you look at these numbers down the bottom here, if you have an SMT-friendly workload and you run SMT1, you're leaving 70% of the performance of that core on the floor, and you don't want to be doing that. So again, you definitely want to be able to use SMT. Now, in terms of dispatching in the shared pool, as I mentioned, the dedicated LPAR has a one-to-one relationship between the core and the virtual processor. In the shared pool, it gets assigned the core at dispatch time. So the first time a virtual processor gets dispatched, the core that it gets dispatched to becomes what we call the home node. And moving forward, we will always try to redispatch to that home node if it's available. So it's always going to try for the same core. All of the SMT threads associated with that virtual processor go with the virtual processor. So if you have 8 threads, all 8 threads go with that virtual processor. You will never see threads for a virtual processor on different cores. The virtual processor is going to run to the end of its entitlement. So in the case we had before of 0.6, it will run for 6 milliseconds, except if it issues an I/O and it has to wait on that I/O, then it will do what we call a seed, and it will give up the core. If it runs out of work to do in 5 milliseconds, it will again do a seed and give up the core. If it's got more work to do and nobody else wants that core, then it will be able to get more core. If it's got more work to do but other virtual processors want the core and they have not reached their entitlement, then this virtual processor will get context switched and it gets put back on the home node run queue. And then if it can't get service in a timely manner, then that virtual processor gets moved up to that global run queue and it looks for another core to run on. And the issue with that is that the data's possibly still going to be in the memory on that home node core. So that's kind of how the dispatching works. That's a very rough overview of it, but it should be enough to give you an understanding. So this is an example that I got from Nigel several years ago, but it actually just sort of illustrates one of the issues with dispatching. So in this case, I've got a single core and I have 6 virtual machines assigned to it. So the virtual processors get dispatched at one after the other. Each one gets their entitlement. Once it has its entitlement, it gives up the core. So when I sum up our 6 virtual machines, let's say that their total that they're going to use is 6 milliseconds. So we have 4 milliseconds left on the core. If you look, I have 1, 2, 3, 4, 5, 6 different virtual machines. So what will happen is the light blue one will run, then the yellow, and then if the light blue one needs more, he'll run again. So if if on average, if we gave the light blue core, virtual machine, a 2 millisecond dispatch window, but he always needs 3, or in this case, let's say 4, then he's always going to run again. And what happens is, if everybody else wants the core, then we look at the weights and we build a ratio, and that is how we determine who gets the core and how long they get it when they've exceeded their entitlement. The issue that you have to keep in mind is, if I look at the light blue one, it gets loaded onto the core, and we warm up the CPU cache, and then as soon as the CPU cache is fully loaded, it runs hot. Then we obviously have to unload the CPU cache so that the next VM can run. But when we get redispatched, again we have to heat up the cache. So basically, I might have taken 4 milliseconds, but I'm not running with a hot cache the whole time, and so you get cache misses. If you know that you're getting a lot of those, then what you're going to want to do is increase your entitlement so that your dispatch window is a little bit longer for that particular virtual machine, so that we consolidate these 3 into one long dispatch window where we're not forever going and having to reload the cache. And that's kind of what I'm talking about here with entitlement MVPs. This is a somewhat long-winded slide, but the whole point of the slide is you can go down and allocate a virtual machine all the way down to a 20th of a core. So I could have 20 virtual processors on a single core LPAR. What that means is that every time something gets dispatched, it's going to get a half a millisecond. It's really not a good idea, because the thing you've got to keep in mind is that means that the hypervisor has to manage 20 virtual processors, plus if you're running SMT8, that's 160 threads that it has to manage for every core. That's an awful lot of hypervisor overhead. The other thing is that if you have an entitlement down that low, and you are running above, and you need to go above your entitlement, if you run all your LPARS like that, you're going to spend a lot of time contending for cores. So be very, very, very careful. The recommendations that I've always gotten from Steve Nasipany and Grover were to stick to more like about 0.6 or 0.7 of your virtual processors. But really what you want to do is figure out what you're using on average, go a little bit above that, and set your entitlement to that. And then set your virtual processors to whatever you need at peak. The one place where you need to be very careful is with your virtual VIO servers and anything that's really dependent on your shared Ethernet adapters or virtual Ethernet, because they scale by entitlement, not virtual processors. And the other thing to keep in mind is that all of the virtual processors that you have to be dispatched before one can be redispatched. So if I have 20 virtual processors, I have to dispatch 1 through 20 before I can redispatch 1. What that means is if you have more virtual processors than you have cores, then you're always going to have virtual processors waiting to be dispatched. And the same applies if you are using the multi-shared processor pool, where you put things into different pools. Let's say you have an IBM I pool and you have 7 cores in it. If you end up assigning an LPAR 9 virtual processors and you only have 7 cores in the pool, at all times 2 virtual processors will be waiting. And that can cause a really bad performance problem. That's what I'm talking about down here in the red. So when you do your upgrades from one server to another, one of the things that people don't do is resize their LPARS. Well, if I'm coming from, in this case, a P740 where I'm around 12 and a bit RPEF per core, and let's say I'm moving, I'll stay with SMT4, let's say I'm moving to a Power 9 S922, I'm getting more than 1.5 times the performance out of that core. So do I really need to give the virtual machine that has 8 cores on the Power 7, 8 cores on the Power 9? Unless you have latent demand, you're going to want to scale back the size of those LPARS. I wouldn't say exactly with the ratio of, this 19.57 over 12.36, but I would definitely scale it back so that you've got more core available to use for other things. And you want to do it LPAR by LPAR. You don't want to do it based on the actual RPerf for the server. That will get you in trouble. And I'll show you an example of what happens later on. If you have too many cores of virtual processors, you're just wasting dispatcher and hypervisor cycles, and that's going to affect your performance. I just have a comment here on capped versus uncapped LPARs. If you cap an LPAR, it can give up unused cycles, but it can never grow above entitlement. There's multiple ways you can cap an LPAR. One is to check the box that says capped. The other one is to give it a weight of 0. A weight of 0 does a soft cap. And the third way is to set your virtual processors to your entitlement. Anytime that you do that, you are basically capping the LPAR and it can't grow. So if you've put it in the shared processor pool so that it can grow and shrink, then capping it takes that away. Now, one of the reasons people do capping is for licensing purposes. And what you can do is simply put them into a shared processor pool that specifically has the number of cores that you're licensed for, and then you can put your LPARs in there and they can compete for those cores. The other thing that you want to keep in mind where people get confused is that max virtual processors and max processor units have nothing to do with capping. All they are is how big you can grow the LPAR with a dynamic LPAR operation. So just keep that in mind. Somebody had asked the question if all your LPARs are over their entitled capacity, but altogether they're consuming less than 90% of the entire managed system CPU. Are they still fighting for CPU allocations? The issue of them being over their entitled capacity, if they're over it most of the time, that's going to be affecting your network performance if you're using a shared Ethernet adapter or if you're using virtual Ethernet. And it will affect it at the clients and at the VIOs. So you would need to look a lot deeper into what that's doing. Plus, if they're consuming, 90%, I'd be a little bit concerned about what would happen if they peak. Now, one of the other things that changed with Power 7 and above is the way virtual processor unfolding worked. So what used to happen was if you were using a virtual processor and the system wasn't particularly busy, let's say you had 4 virtual processors and you were really only using the equivalent to 1 core, it would fold 3 of the virtual processors if they weren't being used. And so everything would get focused onto 1 core. And the way that it allocated the threads, it would load the first thread and the second, or load the first thread to about 80% utilization, the second thread to about 80% utilization, and then it would unfold a virtual processor. So it was very common if you looked at an NMON to see virtual processors folding and unfolding. And they call that scale mode. What we're running now is raw throughput mode as of Power 7. Basically, the first thread on the virtual processor gets loaded to 39%, and then we unfold a virtual processor. So what we're actually doing is we are running the primary thread on every virtual processor will kick off before we kick off any secondaries and before we kick off the tertiaries. So we're putting a primary thread on every core first. It's still the same physical consumption that's being used, but that's one of the reasons why it's important to reduce your virtual processors when you migrate across to a Power 7 or a Power 8, because what we're doing is spreading and stacking instead of what we used to do, which was stack and spread. This will get you the best combination of response time and throughput per thread, but you have to keep in mind that every virtual processor will be used, whereas before they would not. And then there's a slight change in Power 9, where because people were running into issues on their small workloads, Steve Nasipany is going to be talking about this at the PTECU, but basically the dispatcher now tries to take those little tiny workloads and collapse them. So as of Power 9, you may start to see virtual processor folding again. And there's a new command, or new flag on the MPStat, the -v command flag. And what that allows you to do is monitor your virtual processor and SMT activity by looking at this virtual time base. So you can actually see the actual dispatch time for every virtual processor at the physical layer. And Steve goes into that in a lot of detail. So if you are going to the Power TQ, I do recommend that you go to that presentation. Now, in terms of shared processor LPARS, I made some comments before. Your application has no idea that we're using micropartitioning. It just knows that it's running on a core. But if you have applications that have very strong response time requirements, and I'm talking about things that are very latency sensitive, that have polling behavior, the kind of things I'm talking about might be trading applications, where he who gets there first wins. Those don't necessarily behave as well in a shared processor LPAR. Also, some of the CPU-intensive applications, where I've seen it a lot is with SAS. I tend to run my SAS workloads dedicated. And one of the reasons for that is because they tend to be long-running, and they want the core for as long as they can get it. And they also tend to load a lot into the cache. The good candidates for micropartitioning are the typical applications that we run all the time. Our databases, our web applications, mail service, directory services, all that kind of things. So most of the things that you're going to be running, you're going to have no problem with having running in the shared processor pool. But just be aware that not everything will run really, really well. So you may want to, if you have an application like SAS or high performance computing, you may want to try it both ways and see which way performs better. Some general server sizing thoughts. Basically, you've got to look at how much processor power you have, and I mentioned the fact that I like to set my LPARS to have a little bit more entitlement than they need on average, and somewhere that makes sense with their virtual processors. We're going to talk in a minute about memory overhead for page tables, etc. So I'll talk about that under memory. You've got to decide about shared or dedicated, capped or uncapped, and do not starve your VIO servers. This is really important. People would look at what the minimum requirements were for a VIO server, so they'd give it, a couple of gig, or they would only give it one core. You need to actually look at what it really needs, and there's a new command called PART, P-A-R-T, which used to be the Virtualization Advisor. You can run that on your VIO server, and it will actually tell you whether you're undersized. And the thing to keep in mind is that the amount of memory you need, particularly in the VIO server, is going to be dependent on how many high-performance adapters and things like that you have attached, because they actually need additional memory. And as I said, scale by RPerf, and I'm going to give you an example now of why. So what I have seen people do is they've summed up their entitlements, and their entitlements come like down here to 10.3. So they go, okay, I only need like 11 cores for this workload. No, you have to sum it by your concurrent peaks. All right, I might only need 10.3 cores most of the time, but if all my workloads peak at the same time, I need 20.5. So 21 cores. So if I only put 11 cores in this, activated in this server, I would never ever be able to address my peaks. And I've seen so many systems where I've logged on, and when I've summed the entitlements, every core in the box is assigned. And I'm like, so how do you expect to grow at peak times? Just be very, very aware of that. That's something that, because what happens is management will look at it and they will go, well, you're not using all the cores. We paid for all these cores. Why can't we use them? It's like, well, because when all our users log on at peak time, we need to have the resources to meet their needs. So where that also gets you is when the users tend to be very, very sporadic. So you're going to have to run some nmons to figure out when your peak is each day and what your peak is at the end of the month, or at whatever your peak periods are. You may have a specific time of the year that you've got to plan for. You need to have take all those into account, figure out where you'd use some of the capacity on demand options if they're available versus having to have additional cores in the box. Because nobody wants to be shutting down multiple LPARS in order to address the peak needs. So just something to think about. In terms of monitoring a shared processor pool, there's a number of different ways you can monitor it, but the critical thing is this first step, and it is not turned on by default. If you want to get real statistics on how much of the shared processor pool is being used and how much is available, on every LPAR on that server, you need to turn on this allow performance information collection. What you do is you check the box for the LPAR at the HMC, click on properties, and just check this little box. If you don't do that, then you're not going to have valid data, and you need to do it for every LPAR. Then you have multiple ways to look at it. You can run a topaz-C, you can run nmon with the option of P, the nmon analyzer LPAR tab will report back on it, and LPAR-stat reports on it. And every one of those calls it something different. Topaz-C calls it APP for available pool, processor pool. LPAR-stat calls it the same, but that also uses pool size. nmon-P uses pool CPUs, and the nmon analyzer LPAR tab uses something else. Someone asked if allow performance information collection increases CPU usage. I have not noticed that it increased CPU usage at all. So I'm sure it does. It adds a little bit to the hypervisor, but I've not seen any numbers, and I've had it turned on a lot of LPARs and not seen a big issue. I mentioned this emstat command before. I'm not going to go into it except to mention the comment down the bottom. A lot of people bring old binaries across. I see it a lot with Oracle where they don't relink the binaries when they bring it across to a new architecture. There's a reason why Oracle recommends that you do relink the binaries, and it's because of these emulations and alignments. So if you're bringing code across from Power 6 to Power 8, you should be trying to recompile it. It's also why IBM will recommend that you install the latest version of something like a WebSphere or Java or whatever, is to avoid some of these issues. IBM has a very strong binary compatibility statement, and what that binary compatibility statement says that if you have something that works on Power, actually back as far as Power 4, it will work on Power 8 or Power 9, provided it doesn't use certain types of built-in device drivers or hypervisor level commands. You will not see the word performance mentioned in a binary compatibility statement. What people are telling you is it will work. They're not saying it will necessarily perform well. And an indication that it's not performing well is when you see numbers in these alignments and emulations. And I've seen systems where literally in one case they were doing 17 times the amount of I/O that they did on the old system because of the way their code was compiled. When we recompiled it, that went away. So just be aware that if you're bringing old code across, you may run into performance problems even though it works. So now we're going to talk a little bit about memory, and we'll start out by just talking about memory types. Let me start by saying that all paging, and when I say paging, I mean taking pages out to free up memory for other pages, is bad. There's three different kinds of memory. There's the kernel, which is AIX, and it's usually around at least 2 gig, and you don't do anything with that. Then we have persistent and working storage. Persistent memory is basically your file systems. All right, and it is what we call the file cache. So if I read in something from a file system and I don't change it, it's sitting in memory on the system, and if I need to steal a page, I can just take that page and I can always get that page back from the file system. That's what we talk about with persistent memory. Now, if you're using raw devices, GPFS or Oracle ASM, they don't make use of the file cache. What happens with most applications is they'll read whatever it is in, it goes into the file cache, and then they read it into their application area. Oracle does that into the SGA, PGA, etc. When you use raw devices, GPFS, Oracle ASM, things like concurrent I/O, they read it directly into the application space. They do not read it into memory and then copy it to the application space. So the memory is still persistent in that it's backed by a file system, but it does not go through the file cache. Working storage is basically everything else. It's the executable, their work areas, and these are backed by a page space. So when I want to steal a page from working storage, first I have to write it out to a page space. Then I can take that page. So it is more expensive than stealing persistent memory. And working storage will show up as AVM if you do a VM stat. If you take the number of pages it shows under AVM and multiply by 4096, it will give you bytes instead of pages. Or you can look at Nmon Analyzer at the percent computational, or run a vmstat-v and see the percentage of memory used for computational pages. Obviously you want most of the memory to be used for computational versus just for file systems. If that computational gets up very high, and the number that I've been given is near or greater than 97%, you are paging, and the only fix for that is going to be more memory because you got nowhere to steal it from. I tend to start looking at it when it gets closer to 80% because it takes time to raise the case with management to get more memory, so it's not smart to wait till it gets to 90%. All of these, how memory is used, are all affected by 5 parameters: min-perm, max-perm, max client, LAU file repage, and page steal method. And of those, 4 of them are now restricted parameters and you should not be using them. The only one that you're really supposed to tweak if you want to is min-perm. We'll get into what those do. So one other thing I want to mention before we talk about min-perm, etc., is hypervisor overhead. When you set up a server, when you decide how much memory you need, you can't just add up the memory that you need for each LPAR and go, okay, I need 128 gig of memory. The way that memory is allocated to each LPAR is it's basically a virtual memory system. So what that means is the hypervisor takes a certain amount of memory out of real memory, or what we call hypervisor page tables, where it builds a table that says, you know, this LPAR has 0 through 16 gig and they map to these real pages. So it's basically a mapping in the hypervisor page table of that memory. The size for that hypervisor page table, and there's one for every LPAR, is determined by the maximum memory setting for the LPAR, not by the desired. And the reason that it does that is because you could de-LPAR in more memory, and I have to have enough space in that table to be able to accommodate that maximum memory setting. So the moral of the story is, if you have 100 gig in the system and your LPARs are set to 5 gig entitled, don't set the maximum to 100 gig. Set it to something that you might need to grow to with a DLPAR. So if I look at that first one, I'm probably just going to go with 5 gig current, maybe 10 gig maximum, because I don't want to end up holding 2 or 3 gig of real memory for a hypervisor page table for a 5 gig LPAR that I'm never going to grow beyond 10 gig. I mean, that's crazy. So just be aware of that. If you look at an HMCScanner report, one of the things that you'll see in there is how much is actually being used for overhead. So this one here you can see is 13.7 gig, the next one is 23 and 38. It's not uncommon to see large numbers there. I mean, this system has 1.5 terabytes. It has a whole bunch of LPARS. I think it had like 40 LPARS. So I would have to look at all the maximum memory for each of those to figure out whether I had a problem. The other thing is if you have hypervisor memory mirroring on, then the hypervisor memory that is mirrored comes out of the real memory as well. So basically, that firmware overhead includes that mirrored memory. So you shouldn't seeing 38.5 gig shouldn't cause you to have a heart attack, but what you want to do is go and understand why you've got 38.5 gig, and it may be perfectly normal. I have a spreadsheet that I use to calculate all this. The the one comment I'll make that's missing down here under the divisor is that if you are running IBM I, it's actually 64. And if you're running anything prior to P7 Plus, it's 64. So I've got IBM I up here. Basically, I go into the spreadsheet and I fill in a bunch of details, and then I go through, put all my maximum memory into my LPARS. If you look, and then it calculates what the overhead is. It's rough, but it's close enough. So here, if I add my desired memory, I have 185 gig. When I actually look, when I add on all the overhead, I actually need closer to 203 gig, which is 13 gig more. So if I'd only activated 185 gig, I would have to be taking memory from somebody. And effectively, this here is the actual overhead that's calculated for the page frame tables. So for my 4 gig maximum setting here, I basically need 256 meg to hold those page tables and so on. So you can imagine if I had made that 16 gig for the maximum on a 3 gig LPAR, I'd be holding a gig. All right. The other thing is that every high performance port, so that's every 8 gig fiber port that is active, every 10 gig or 16 gig or whatever network card port that is active, has an overhead of, I think it's 512 meg. So you have to calculate that in. And then for every NPIV virtual fiber channel, so that's every NPIV client, and if you've got 4 connections to a client through a VIO, that counts as 4, also has 102 meg. So you basically have to add all those in on the VIOs to figure out A, how much memory you need on the VIO, and then secondarily what your real memory overhead is. So there's calculations that you should do to make sure you have enough real memory, even though, as I said, your desired memory is only 185. And you can get similar numbers from the system planning tool, etc. So the question is, do vSCSI connections have an estimated memory requirement? So the vSCSI memory requirements come out of the extra high performance ports, because like you're going to have an 8 gig fiber adapter, so that's going to require, what is it, 512 meg for each active port. So if you've got 2 active ports, that's a gig, and that covers your vSCSIs. So I talked about min perm, max perm, etc. So the reason I bring this up, even though hopefully none of you are still running AIX 5.3, is that by default we used to have to tune these on 5.3, and if you migrated your system from version 5 to version 6 or version 7, those tunables will have come across. So the way that it used to work was if file systems were using more than 3% of memory, the idea was we'd always try to steal from file systems. Then we have max perm, which is a soft cap on the memory that file systems or network can use. So if file systems exceed max perm, we're always going to steal from file systems as well. The issue was that the gap between min perm and max perm, it actually went through and did a whole lot of algorithms, etc., to figure out who it would really steal from. If it was below min perm, it was always executables. Now, max client has a hard cap, and it is a subset of max perm, and it only impacts JFS2 and NFS, I think Veritas. I have to check that. So what people would do was they would reduce max perm and max client, because by default when you reduce max perm, you reduce max client. So they might have min perm 3 and max perm of 20. And what that would do is, if you're using JFS, it would say, as long as my file systems are using less than 20%, I'm not going to steal from them, or I'm going to at least go through the calculation. Above 20%, I'll let file systems use that space, but if executables need it, then I'll steal from file systems. So that's what you wanted to do. The issue came about when we moved to JFS 2, and JFS 2 was dependent on max client, which is a hard limit. And so suddenly people found when they moved to JFS 2 that they were paging, yet they had available memory. And that was because their file systems couldn't use more than 20%. Well, when they can't get the memory for their file system, they get paged out so somebody else can run. All right. So one of the ways they chose to get rid of the calculation piece between min perm and max perm was they came out with something called LAU file repage. And LAU file repage by default was 1, and they changed it to 0. And what that did was it said, forget about this calculation. Basically, we'll still have min perm, and max client, but in terms of my calculations, if file systems are using less than min perm, we'll steal from executables. If file systems are using more than min perm, we will make a strong recommendation to the LAU daemon to always steal from file systems. Well, that was fine, but people put that in and they saw some interesting improvements. The problem was nobody told them to increase max perm and max client up to 90%. And because they didn't do that, they still had that hard cap. Now, max perm, max client are both restricted tunables, so they should not be in your system anyway. They should be left to default to 90. Depending on which technology level you're running in version 7, you may or may not see LAU file repage, but it is now a restricted tunable if you do see it. On version 6 and 7, these are set correctly by default. If you change them to something else, and you raise a perf PMR with IBM, they're going to tell you to change it back before they will look at the problem, because good chance it's causing the problem. And I have seen people where they have put these back to the default and put the other two that we're going to talk about in a minute back to the default, and paging problems have disappeared because they were causing their own paging problems. So I always tell people, look at Etsy Tunables next boot and make sure that you don't see any of these in there. If you have changed them, and I've seen people where they had a DB2 PMR 8 years ago, where they got told to change them, and then they've upgraded DB2 and the operating system and everything else since. You need to have a good reason why, and I recommend to people that they keep the output from any PMR that tells them to change it, because you're probably going to get told to change it back. Now, the other two that impact it are page steal method, and so we're going to talk about a page steal method, and then we'll talk about some page space things. So page steal method, again, the default in version 5 was different to 6 and 7, but if you had hard coded it, it's going to be in your tunables. So we set LAU file repage to 0, basically telling the LAU daemon to pretty much try and steal from file systems. Now, one of the things that happens in the system is that when you bring it up, your memory is divided into memory pools. So there were some bugs early on with that, but now most of those have gone away. So effectively, let's say you have 400 gig, and the system decides that you've got 10 memory pools. That means you have 10 pools, each around 40 gig. And those memory pools have to be managed, because obviously if we want to steal pages, etc., the LAU daemon has to go and do that. Every memory pool has its own LAU daemon. So if you see that you have 10 memory pools, it would not be uncommon to see 10 things in the run queue, each of which would be an LAU daemon. So when the LAU daemon manages a memory pool, it has two different ways to scan for free pages. If page steal method is set to 0, it will scan all the pages. So it's going to scan all your file system pages and all your executable pages. They're just going to be in one big pool as it tries to free pages. Well, we're trying to steal primarily from file systems, so wouldn't it be smarter to basically scan all your CPU ones, your file system ones first. That's what page steal method 1 does. It says scan only the file system pages. Now, if I can't get enough memory out of those, then I'm going to go and scan the others. But it creates two lists in the pool, one of file system pages and one of CPU pages or executable pages. This cuts down on the CPU used by scanning because you're not scanning pages that you're not going to try to free. You combine it with something like concurrent I/O, it cuts your CPU and it also will reduce the amount of memory that's used. And as I said, by default, in 6 and 7 it is set correctly. But if you did a migration from version 5 or somebody reset that value, then you're going to be causing yourself problems. So again, you want to look in Etsy Tunables next boot and make sure that none of those are in there because they are restricted and they will cause you a problem. So we're going to talk quickly about page spaces. When you're setting up page spaces in the system, you should, firstly, any page space that's on internal disk needs to be mirrored to another internal disk. If it's on the SAN, it's going to be rated, so you don't need to worry about that. I don't care if your page spaces are on internal disk or on the SAN. What I care about is that you have enough page space to deal with the workload that you're running. And the thing to keep in mind is there's some best practices around setting up page spaces. When you're paging, the system will tend to, if you've got more than one page space, it does a couple of things. Firstly, it will try to page in and out in parallel, and then secondarily, it will round robin. So what that means is if you do what some people do and you have a very small HD6, say 512 meg, and then you add a paging 00 on another disk, that's 16 gig. Once you start to do any paging, HD6 will fill up very quickly. Now, there have been some changes over time. It used to be that if that happened, since the only place kernel pages could go was HD6, the system would quite likely crash. What they changed is that kernel pages can now go outside of root VG. So what you're doing now is you're slowing down paging. If my HD6 is 100% full all the time because it's really small, and my paging 00 and paging 01 are much bigger, and pages can go there, pretty much what's going to happen is as it round robins around, every time it hits HD6, it's going to say, oh, it's full, and then it's going to have to redrive that page operation. So not only are you paging, you just slowed it down. So you want to have multiple page spaces if you can, and you want to make sure that they're all the same size. If you cannot make HD6 as big as the others, one of the options you can do is swap it off after you reboot. The other thing to keep in mind is you do not want your page spaces on the same HDisk as each other. And an example of this is the default setting for the VIO servers, which I've been complaining about for years. Prior to 226, there's a 512 meg HD6 and a 1 gig paging 00. As of 22620, it's two 1 gig files. And they're usually on internal disks. So if you do start to page, well, number one, it's bad. But if you do start to page on your VIO server, they're on the same disk, which means the CCAR is going to be moving to and fro. Additionally, what you run into is queue depth issues where, since all that I/O is going through one HDisk instead of maybe being shared across three, you're going to run into some queuing issues. So all real paging is bad, but there are things you can do with your page setup that make it worse. And what I'm trying to tell you here is don't do that. A couple of things about memory problems. You can look at your computational memory use. As I said, it'll show as AVM, or if you look at an M1 analyzer percent comp, or again as a percentage of memory. And we already talked about if it's near 97%. If you want to find out who's using all your page space, you can run svmon, and this is basically saying, I want you to tell me in megabytes the list of processes and who's using the most page space. And there's various things you can put in that sort seg to figure out who's doing what. All right, some of the things that you could do in terms of looking for problems. LSS-RAD-AV, that lets you look for affinity issues that we'll talk about in a minute. The MPStat-D is going to show you all your SMT threads and what they're up to. Sorry, it's going to show you the same affinity stuff. VMstat-V, we'll talk about that a little bit more in I/O, and so on. So in terms of affinity, there is a difference in performance when something's running on a core as to whether it's getting its memory from that chip, from the same processor board, from a different socket, or from a different node. And depending on the box, you'll hear them referred to as local, near, and far SRADs. So on an 814, which is a single processor board, local is the same chip. Near is actually the same socket, and far is would be a different socket, but it doesn't have a different socket. So you would always see 0 there. If you're dealing with something like a 980, then it's more like what I have here, which is within the same chip or socket, within the same node, and internode. And if you ever look at IBM's bandwidth publications, you will see they refer to intranode and internode gigabytes per second. And internode, where you go across to another node, performs significantly slower. It's not that it's slow, but it's much slower to go across a node to get memory than it is to do it within the node. And that's why some of the companies like Epic for the medical stuff has restricted setting up their software on single node systems. And the reason for that is that they guarantee performance, and it's hard to guarantee performance if you are going across nodes. This is also why when you're using these multi-socket and internode systems, sizing your LPARS becomes important. So as an example, if your socket is a 16-core socket, if you can keep your LPARS to 16 cores or less, you have a much better chance that that LPAR is going to be assigned 16 cores on the same socket, which means that initially it will get signed the memory DIMMs that go with those cores, and you're going to get better performance than if you go to that 17th core and now you've always got at least one core on a different node. There's firmware, etc. requirements on doing this, but just be aware that that's something you want to think about. If you look at an MPStat-D, so this is on an E880, which is a multi-node. They have very meaningful names. S3HRD is your locals, S4HRD is your near, and S5HRD is your far. So this is actually not a bad layout for this. You know, if I look at CPU 0, which is thread 0, 83% of the time it's local, and so on. What you don't want to see is stuff that's more like this down the bottom, or where these are flipped, where 100% of the time it's far, and so on. So you can look at those and remember, as with all stat commands, this is since boot. The vmstat-v command will actually tell you how many memory pools you have. I just didn't put it on this one. It tells me a number of issues to do with blocking. Now again, this is since boot. So if this system was booted a year ago, these numbers don't really have a lot of validity. So what you want to do is run a vmstat-v maybe in the morning and a vmstat-v in the afternoon and see if these numbers are increasing, subtract one from the other and figure out the ratio. Because as an example, I happen to know this system was only booted 2 or 3 days beforehand, so these numbers are very bad. So what this is saying is that there were 1.4 million pending disk IOs blocked with no PBUF. Now PBUF is a pinned memory buffer that is assigned, and the group of PBUFs is assigned per volume group. And the default is that there are 512 PBUFs for every H disk in that volume group. Those PBUFs are used to build IO requests. So when I want to issue an IO, I go and I ask for a PBUF and I build that IO in however many PBUFs I need. I then analyze that IO and figure out where it goes next. Is it a page space IO? In that case, it goes to a page space buffer. Is it JFS? In that case, it goes to a JFS FS buff. Is it NFS or Veritas? Now it goes to a client one. Is it JFS2? It goes to one that's called an external file system buffer. So you can see the system was not having a good time. It had 11 million times that it tried to build a page space I/O to go out or come in from a page space, and it could not get a buffer, which meant that it had to sit in the pbuff. We also had an issue with JFS2. There were almost 40 million of them. Like I said, if this had been in the last year, you wouldn't be able to tell. But since it was only 3 days, I know sometime in the last 3 days I've had a really big problem. It is not uncommon, even if you have no JFS in the system, to see somewhere around 2,000 there. So if that's the number you see, just ignore it. But the others you want to pay attention to. So this system was obviously having paging problems, and its pbuffs needed reviewing and so on. And we don't tune pbuffs the way we used to. We now run the LVMO command, and we figure out which volume group has the problem, and we increase the pbuffs for only that volume group. Because again, these are pinned memory buffers, so we don't want to allocate them unnecessarily. So the other thing I want to talk about is min-free and max-free and memory pools. So what a lot of people will do is they know that they've got, by default, min-free is 960, max-free is 1088. The difference between them is 128, which happens to coincide with the default for JFS2, max page read ahead. The idea being that if somebody does a 128-page read, you don't want to have them send you from a healthy position into a page thrashing situation. So the rule of thumb used to be that if the amount of free memory pages was greater than max free, then you were fine. If it was between min free and max free, then we start page stealing, and then if it's below min free, we're page thrashing, which usually means we're going to go down. The thing that people need to take into account, though, is that min free and max free apply per memory pool. So when you see a number like this in free that says 9902, and you've got max free set to 2000 and min free to 960, you might think you're healthy. But I have to divide that by 10 because I have 10 memory pools. So actually, I only have 990 pages free in each pool on average. That 990 is between 960 and 2000, which means I'm constantly page stealing. And if you look here at the PIPO, you can see there's a little bit of page in, page out going on. The system got worse actually not long after this. But I just wanted to show you, that you need to take that memory pools into account. I tend to calculate min-free and max-free for my LPARS. I'm not going to go into the calculation. Suffice it to say that it's based on logical CPUs and your JFS2 max page read ahead. Logical CPUs being the SMT threads. And it shows as LCPU in a VMstat. So when it comes back with a number like 1472, I'll bump it to like 1536. I like using the powers of 2. I've seen different recommendations. They don't want you to have a huge gap between min-free and max-free, because if you over-allocate it, you're going to see some high values in free, but you can be paging because the system's busy stealing because you told it that it had to keep 10,000 pages free. So just be a little careful with those values. I'm pretty conservative, but I do actually modify them. The other thing, and those are one of the few things you'll see in my next boot for performance. The other thing to keep in mind too is if you bump JFS2 max page read ahead from 128, that's part of this calculation. So this would end up being a higher number. Right. So we're going to talk really quickly about I/O and network, and then I'm going to have to go through these very, very quickly. The thing I want to basically take you through is what really happens with an I/O request. So the logical volume manager is going to request a pin memory buffer to hold that I/O request. We then place it into a file system buffer. If I'm paging, I go get a page space buffer, otherwise I get a file system one. That I/O then gets queued to an H disk. That queue is what we refer to as queue depth. Each H disk has a queue that you can queue things to. Then we queue it to an adapter. The name of that is num command alums. It's kind of like queue depth for an adapter. Finally, it gets queued to the disk subsystem. And then additionally, every 60 seconds, the sync daemon runs, and his job is to go through and look at the IOs that are dirty, so pages that have been modified that need to go out to file systems or page space. So sometimes you'll see a spike in IO out to them every 60 seconds, and that's the sync daemon doing its job. The sync daemon is not used in the case of uh, raw disks. It's also not used with GPFS or concurrent IO, and I think Oracle ASM doesn't use it either. So a couple of basics about IO tuning. There's not a lot of tunables you really set for IO. Um, the big killer is data layout. If people put all their stuff that's really, really busy on one H disk, they're going to kill performance. You know, I feel very strongly about the size of H disks. I've had many arguments with storage admins who say, we've got the storage system that's just amazing, it performs really well, it's got SSDs and cache and all kinds of things, so we're just going to give you a couple of 2 terabyte LUNs. And I'm like, no thank you, because IO performance is about bandwidth and queuing. It's not about size. So you can give me a 2 terabyte LUN, but if I put all of my redo logs and data and everything on the same H disk, I'm going to have a horrible performance problem, because those I only have one queue for that H disk. So everything's going to be queued to that one H disk, and there's a maximum size for that queue. Versus if I have maybe take that 2 terabytes and divide it into 8 H disks, now I've got 8 queues and I can spread my data around. I can separate out, redo logs from actual data so they're not impacting each other and so on. The other thing to keep in mind with larger LUN sizes, so if I have a 2 terabyte LUN, I'm going to have larger PP sizes. And that is not great if I have a lot of little file systems. And then there's a bunch of stuff down here about queue depth. Just be aware that multipath divers will enforce queue depth IOs. So you don't have a way around it. Oops. The other comment I want to make is on IO wait. A lot of people think that IO wait is actually helpful. IO wait can actually be very, very misleading. It's a form of idle time, and basically all it is the amount of time that there was an idle CPU and there was an IO outstanding started from that CPU. So the problem is, if I've got a busy system, that CPU may never be idle, because as soon as I do an IO and give up the CPU, somebody else runs on it. So I could see no IO wait and actually have a lot of IO wait, because the CPU is actually executing things. It's just not executing me because I'm waiting. So just be a little bit aware that IO wait can be very misleading. You can certainly use it as an indicator that you need to look at other things, but don't go and tell people that you've got a really bad IO wait situation because you're seeing 40% IO wait, when in fact there actually isn't any IO wait, or there is some IO wait but it's not major. There's a whole bunch of diagrams and things that I don't have the time to go into in this session. So I'm just sort of giving you the warning that it can be misleading. I've already talked about queue depth, so I'm going to very quickly touch on some of the disk adapter sharing options. There is a difference between vSCSI and import and MPIV, or import virtualization, that you should understand. In the case of vSCSI, all the zoning is done to the actual physical fiber channel adapter to the VIO server. The VIO server then basically takes all those disks and it actually sends them over to different LPARS as generic SCSI disks. All the multipath drivers run in the VIO server. The problem with that is that you have to keep spreadsheets of which disks go where, and security people get a little bent out of shape because they have this theory that the VIO server can see all the disks to all the LPARS. NPIV, on the other hand, is a pass-through. So we don't zone the actual fiber channel adapter here, we zone the virtual fiber channel adapters that we define for that LPAR and the HMC. And as it's a complete pass-through, the VIO server never sees the disks. The disks are only seen at the LPAR, and so they run as like a regular fiber channel disk. That means that any multipath drivers need to be in the client LPAR. Then the last comment I want to make on I/O is about something called a demoted I/O. If your applications people are writing applications to a specific block size, let's say they use 1K, but the file systems are at a 4K block size, and we see this with Oracle Redo because Oracle Redo logs are 512 bytes. If you don't change either the file system block size or the application block size, what will happen is I try to write a 1K block size, and the file system says, well, I'm actually 4K, so I have to redrive that I/O. We call that a demoted I/O, and here I have how you can trace it with for JFS2 and what to look for. So someone asked the question, which runs faster, MPIV or vSCSI? I personally think MPIV runs faster, but you'd have to do your own measurements because it depends what the back end is. If you're doing NPIV from a slow disk subsystem and vSCSI from a fast disk subsystem, that's all going to change. All right. Okay, getting close on time here. So a couple of comments. So you can run your virtual Ethernet and your shared Ethernet adapter with and without tagging. The comment that I really want to get through here is two things. The first thing is, if you look, your shared Ethernet adapter under the covers uses virtual Ethernet. Between all these LPARS, it's a virtual Ethernet, and then they connect to the shared Ethernet adapter and go outside on the physical adapter. So just be very aware of that, because remember I said that the entitlement, the amount of CPU in all these LPARS impacts this virtual Ethernet. So if you don't have enough CPU, this virtual Ethernet, there's not enough CPU here to actually run that virtual Ethernet. Just keep in mind. Another thing that a lot of people aren't aware of is that as of VIO server 223, we don't have to define the control channel anymore. And in fact, we don't define it, so we don't have to go off and beg for a VLAN number from our network people. By default, if you do not define the control channel, it will use VLAN 4095. And I switched to using that as soon as 223 came out, because if you want to run multiple SEAs, you're forever begging for VLANs from the network people. This way, we just say to them, you can't use 4095, and we'll use that. And multiple SEAs on the same system can share VLAN 4095. A couple of comments on adapter settings. So if you run the NO command, by default, your TCP send and receive, UDP send and receive, and RFC 1323 are all set as if it was a 10 meg network. You should go and change those defaults. And even if you are going to individually tune the adapters, you should still change the defaults, because if you miss one, they will default to these very, very low values. The other thing that happens is when you first define the adapters, by default, the system decides to help you, and it will sometimes hard code values on the Ethernet adapter. So basically, I'm limited to 64K for TCP send and receive, and RFC 13230, which means I can't use more than 64K for my window size anyway. I want these to be more like 262144, which is 256K. So my starting point is always to set those to that. My NO command, I set them to these, but I also, on the adapter, when I'm in a situation like here where it's already been overwritten, I hard code it with the chdev command, and unfortunately it does require a reboot. Alright, so just be aware of that. There's a number of things that you can do with the virtual Ethernet. We don't really have time to go into those today, but one of the comments that I would make is that if you have a VIO server that handles your storage and a different VIO server that handles your network only, you can actually disable threading. By default, Ethernet has precedence over virtual SCSI and storage. So when you're running them both in the same VIO server, you need to let the threading default so that they each get a fair share. If it's only handling the network because you've got your storage going through a different VIO server, then that's when you could turn off the threading. And there's a number of links here about all that. And that's what I'm getting at here with threaded versus interrupt mode. And I've already addressed the control channel. The last thing about the network that I want to talk about is, remember it's a virtual Ethernet behind the scenes. So you need to look at your use the netstat-v command and look at what's actually happening on your virtual Ethernets, because one of the things that you may see is drop packets, no resource errors, and hypervisor receive failures. Now you see this on the SEA, and you'll also see it on your actual virtual Ethernets that are defined. And what this means is that because it's not a real adapter, it doesn't have built-in memory. So it goes and builds some virtual virtual Ethernet buffers in the system. And those virtual Ethernet buffers are not set particularly large. So if you've got a lot of network traffic, then I can't. These no resource errors mean that I don't have enough memory in order to get my buffer space vented. They don't necessarily have to be equal. Like the three of these happen to match. They don't necessarily have to match, but when you're seeing numbers in here that are growing, you should pay attention. So you'd scroll down to each of your virtual Ethernets and look at your virtual trunk statistics. And in those virtual trunk statistics, what you're interested in is minimum, maximum, and max allocated. So if my max, I meant to fix that, that's actually offset. If my max allocated is 2048, let me see if I can fix that. There we go. Yeah, if my max allocated here is 2048 and my maximum is 2048, that means I ran out of these buffers. The other thing that will happen is if I run out of small buffers, then the next time I try to get a small buffer, I'll actually get a medium buffer. So it's not uncommon if one of these is maxed out that they all are. In this case, that didn't happen, but you can increase these, and you can increase them. The maximum for small is 4096, and so on. One of the things to keep in mind is there was a change at AIX 7.2, and that change was to something called buff mode, and they changed buff mode so that min was always equal to max. The problem with doing that is you then never know if you have a problem, because if my min is always 2048 and my max is always 2048, it's always going to show 2048 allocated, because the minimum number of buffers it's going to grab is the min. So I always try to have those with slightly different numbers, and I change that buff mode back to min. That's a personal preference thing, but I like to know if I have a problem versus just taking a punt. Right. So a couple of things on staying current, and then we should be done. So in order to avoid problems, one of the reasons I say stay current is the stuff that I was talking about emulations and alignments. If you are running back-level Java, or you're bringing old code across, you're running old versions of WebSphere, etc., then you should expect to see performance problems. So that's one of the reasons why they have minimum levels of things that they recommend or require for the different architectures. And a lot of it has to do with things having been recompiled for those architectures. In terms of monitoring things, we talked about looking at your error report, making sure that you've got all your patches on, keeping your firmware up to date. I remember looking at a dispatching issue that a client was having, and their firmware was about 7 levels behind. And when we actually went and had a look, 5 levels above where they were was the fix for the firmware for the problem that they were having with dispatching. So if you start to have a performance problem, you may want to go and look at the firmware history for your server, look at the level you're at, and then look at all the things that have been brought in since then to see if they've fixed your problem. We talked about architecture, we talked about baselines. Don't underestimate the value of documentation. Also, if you're bringing in new disks, you cannot mix 512 and 4K disks in a volume group, and all the new disks that are coming out are 4K. I have here just some starter sets of tunables, what you would have in 5.3. This is pretty much what I would do for CPU and memory in my AIX 6 and 7. So you might see something that says min-free and max-free settings in my next boot. This is some of the tunables that you may end up changing for your I/O. So this one here is your max page read ahead. If you are doing file system caching, you might want to make it 256 or something else. And If you're running out of JFS2 buffers, we no longer choose this J2N buffer per pager device, which is what we did. That is now restricted. The equivalent for that now is this dynamic buffer pre-allocation. And then lastly, for the network, these are the 5 that I always set for my network. This one here, the UDP send space, can't go above 64K. The other ones can be larger depending on what you need. All right. So I want to thank you for your time. And Joe, it's pretty clear I can't do this in 60 minutes.
That's for sure. You have a hard time in 90 minutes, Jackie.
Yeah, I know.
Yeah. So, you know, a lot of information there, and I think it's pretty clear what I said at the beginning about even if you've been doing this a while, there's something to learn because you covered a lot of different things to look at and to tune and information in this. Really appreciate that, Jackie.
Oh, you're welcome. It's a privilege, and thank you for letting me talk. I hope people.
And so we didn't have really time to go over questions. One of the ones that I'm going to just throw out at you though was the spreadsheet you mentioned. There were some people that asked if that was if that was available. Yeah,
there's a link on the page to where you can download it from the web.
Where you can download that. Well, how cool is that? So all the presentation materials that Jackie's went over today are on the Power Systems VUG wiki. So you can go to the wiki and you can download those. And the wiki site, I put it in the chat in the questions here once, and it's on all the emails you get from me. So you can go there and you can download the presentation. And I have recorded this, so I will put a link to the recording up as soon as I get a chance to upload it and all of that. So that'll be a day or two for that.
And Joe, if you want to take the link for that spreadsheet and just put it below the presentation, that's fine too. That way
okay. Yeah, I can do that. I'll go ahead and do that on the wiki. That'll make it easier. Sure, and a little bit clearer. Yeah, I can do that.
Yeah, someone mentioned shared storage pool performance tuning would be good. Nigel Griffiths is the expert on that. I don't use shared storage pools, but I do know that he covers that in his VIO Server 3.1 presentation, which I know he's giving at TechU.
So I'll have to get hold of him to do another session for us. It's always good to have Nigel. And he did talk about shared storage pools once for us, and that was a while ago. So that would be good.
Yeah,
all right.
There's been a lot of updates, so.
Oh, yeah. Well, with that, thank you very much, Jackie. Really appreciate your willingness to do this and as a trial run for you, and hope it helped you as well.
No, it was good, actually. I always enjoy speaking to the group, and I enjoy attending the sessions. So, yeah, thank you very much.
Good, appreciate it. And for everybody, thank you for joining today. And I'll get invites out for the April VUG soon, and for the April VUG too soon. And with that, have a great month.
Thanks, Joe.
Yep, thank you.